One of our minions has made a number of valuable contributions to the Chaos Project, and therefore I am obligated to bestow accommodations and recognition for his tireless efforts to the cause. So today I'd like to cover one of those topics, which is optimizing your code for speed. Now, first, I would like to posthumously thank the late Steve Jobs, without whom my wife and I might not have been able to afford the high quality tech education that we did for pennies on the dollar. Yeah. He was an alumni at the community college that she and I attended. I believe they built this entire wing. Yeah. Why is it going all fast now? It wasn't before. Let me reload. Yeah. Yeah, the tech center at De Anza, and I'd go to school there. She and I, when Apple went colossal, they poured tons of money into the college, most of which was filtered into the back pockets of the faculty, of course, but there was enough of it around that some of it actually trickled down to the educational level, and we were able to get a high-quality Silicon Valley education for the unheard of $8 a unit. I'm sure you're all aware how the high cost of education in America paves the way for predatory lenders and all. But I don't recall seeing so much of that at De Anza, But boy, over at Noam Chomsky's stomping ground, boy, the University of Massachusetts, they had lines of tables on day one, registration day, handing out credit cards to students. There ought to be a law. But I worked at a coffee house, and she had a bookstore. But literally, we could have picked up cans off the street. You know what I'm saying? And drop them off at the recycling center on the way to school, and then take our bicycles on the train out to Sunnyvale. And yes, we still have one or two trains left in America, and pay our entire college tuition for the semester. Sorry, getting a little emotional here. And of course, as you all know, Bill Gates drove him to an early grave, and I'll never forgive him for that. When you spend your life working to build an empire and some backstabbing, greedy snakes steal it all in the middle of the night, yeah, I could see how that could give anyone an ulcer. I wouldn't give him all the credit, though. According to some of my inside sources at the Bohemian Grove, Pepsi Cola, of all people, also had a hand in that as well. But a great debt of gratitude, not only to Steve, but also this guy here. Steve Wozniak also went to De Anza College. Here seen graduating from Berkeley, where he later went on to go there. And every day we walked out of our classes, more than one. They were dirt cheap. And on the way to the cafeteria, in a display case, was an original Apple computer, like something like that. Wow, talk about inspiration. You see that every day. It's like, and on the way to the cafeteria, there it is. The original Apple computer, along with that Steve and his small band of minions made, Steve Wozniak, along with the journal in his own handwriting with the code for implementing BASIC. But I can still thank him. He's still alive and with us today. I see him from time to time, if I'm not mistaken, walking around with his wife around the French Quarter Fest. Obviously a cat who knows when and where to have a good time. So, tip of the hat to you, Steve. My wife and I would love to extend an invitation to you and your wife to have dinner with us next time you're in New Orleans. We have so much to talk about. That'd be great. So much appreciated to both you guys, Steve and Steve. We wouldn't be where we are today without you. Okay, so one of our fellow minions submits the following code example and suggests that this runs faster. That's very interesting. So I'd like to explore this somewhat. First, we'll need to port this over to Chaos Assembly. All right, so let's first, I'm going to open a similar file that we have done historically here, the pixel, where I used multiplication to determine the address of DI. Whereas here he's using a shift binary shift to achieve the same things. So the theory being that using a shift register uses less clock cycles than doing multiplication. Okay, very interesting. So we will then, well, first, let's get this ported over to chaos assembly, right? So, very first thing, why don't we start by establishing some vars, I guess. Yar. I say, we'll start with our color. Not totally necessary for this tutorial, but what the heck? Color Charlie. Char. How about just DB color? There we go. Good. Make him. Make that. Okay, there we go. So, there's our Charlie color. We shall know then. You can put that in there. So that would replace this. Okay, yeah. We are moving our char color into there. However, I don't think we can directly do that, can we? Let's find out. Can we just move that straight in there? Let us see. I'm just going to comment that out. Let's find out. Let us explore it. What is that? Is something else? I did the bad, the big bad. Control A, Control C. Let me undo all. Mark this as read only, so this does not happen in the future. Go to test. Control A, Control V. There we go. Okay, back to where we started. Okay, we want to see if this works for starters. Let's see what we got. What did I just do? Control A, Control V. Save. I see. I think I bumped something. Okay, it's all saved. One more try. Invalid on 10. What's going on 10? It doesn't like that. Yeah, so we'll go back to the other method and copy that and undo. Whoops, I didn't want that undo. I want to redo. I'm just going to put this instead, copy it and put it there. Yeah, and then I'll copy that and put it there. There, okay. See if that is more effective, shall we? Did something. Where's our pixel? Why is it not printing out? What did we do wrong? Alright, minions. Why won't it recognize our variable? Okay, we haven't set our orgy here. Yeah. First we have to have an orgy. Yay! Oh, X. Was it 7? CO. There we go. Now, what do we get? What do we get? There's our pixel. Yeah, there's our character. Okay. It's actually color pix. I don't care. Okay, so, we got that going. Let's continue hacking some more, shall we? Let's get some position. Okay, hang on. There. Here he's using x minus position, y minus position. Okay, let's get that in there. I will go pose. Start with the x, I guess. That will be DW. DW doesn't have to be, but let's keep it simple here. X's, I'll just say 4. Okay. Okay, so that's in there. That should mean, let me see, can I just then replace DI with X? Let's see what happens if I just get rid of all this here with this, that, and the other. Okay. Let us explore further. This is fun. Okay. Okay, there we go. I got it. It is 4 over in x. Okay, got that working. The x. Okay, so now let's get that y happening, shall we? Why? Because I want to make this a y. There we go. Let's get that in there. So we're going to do a bit of math on it, I guess. Let's see. We got this moved in. Okay, so the way, we're relying on this method here, aren't we? Move SI, Y position. Okay, let's get that happening here. That would be right after here. Yeah. Move SI Y because there. Okay, there's move SI. Move BX. The same thing. Oh, interesting. Okay, so let me just do the same here. Okay, so we are splitting the value into 2 parts. And let's continue here. So then we'll do a little shifty action on that. First we'll shift BX over 8. Now see, the thing here is we can't take a single value and use the shift register on that because it doesn't, 320 is what we're dividing. It doesn't divide evenly using a single number. So what he's doing here, essentially, it's explained. First, doing the y times 256 right here. That essentially is moving, shifting it left is the same as if you move left 1 time, that's 2, 4, 8, 16, 32, 64, 128, 256. See? Okay. So that takes care of that. And then you can't, you'll go over if you through the 320 mark. If you go again, it'll go 512. See, that don't work. So then he splits it into 2 parts and multiplies it, the original value once again by 64 here. You see, using fewer left shifts. It's not the same if you go 7 here and 7 there. Math does not work that way. But okay, so the 2 of these together should now be our desired value. Okay, so then let's get that in there. While we're talking about it, shall we? We got our BX and SI here. SI there. Okay, so everything is moved. Now we'll want to add them together. We're going to go LEA DI. So that will add that in there to DI directly. In the brackets, we're going to say BX plus SI in there. Yeah, so that adds the 2 values together, and then we'll just add DI. Oh, wait. Okay, let's go with that. Let's go with that for the moment. Let's go ahead. Continue. We're not going to do that any longer. That was just for a quickie reference. Now we will add DI, our position X, this value here, in there, our position X, there. Okay, color char. Okay. And now this is interesting too. Quite interesting. Noun's a person, place, or thing. Yes. That here I have used an index method. Over here he's done exactly the same thing using only a single command, which I had searched all over for this. I knew it had to be somewhere, there it is. This is normally used for strings, and what it does is allows you to iterate through a string one character at a time. So when you call STOSB, it essentially is the same thing as this. We've established that our ES is here. So while it doesn't, here, so now I can, to make a long story short, I can STOSB that, and it should do the same thing as using our segment offset. Yeah. So this points to the same thing. The only thing I should mention is when you call this, since it's for iterating through strings, when you call this, it will increment the value of di by 1. Okay. However, if we're using it in a loop over and over, we will keep writing over and over di, so that doesn't concern us too much, So it's just an alternate way of using this command. Okay. So let's see if we have something that works. Okay. We do, in fact. Yeah. So this method replaces, hang on one second here, let me grab the old method. Okay. There. Yeah. So before we took our y position, multiplied it by a value of 320. Yeah, so a little shorter, but in theory, this should use, let me go back. Oops, hang on, I think I got one thing wrong. This should not be 8. This should, in fact, be 6. Yeah. Okay, I'm glad I caught that. I did mention you can't just go 7 and 7. It's not the same as going 8 and 6. You have to. Okay, so there we go. That should. Yeah, I don't know. Oh, I see what I did. Okay, it's all working. Just verifying. Yes, it should be 10 down and 4 over. 10 down in y, 4 over in x. All working properly. Okay, so you want to save that benchmark 1. Or what do we got here? This is a new method of drawing a pixel using shift register. So pixel shift left is probably a good name if you want to save that as a reference. Yeah. So next, we want to know, if this runs faster, well, by how much, So I'm going to set up a little benchmark is what I'm going to do. Okay, once again, you probably want to have saved this as your shift left pixel, or pixel shift left, and then the counterpart, once again, just to clarify, here is the other method using direct multiplication. Okay, save that out also as a pixel using direct multiplication. Pixel mult, whatever, mult, M-U-L, I don't care. You don't even have to save them, but these references can definitely come in handy later. Okay, so now I'm going to prepare a benchmark program. Okay, I think all I really need to save, for starters, I'm not going to need any of this code. Okay, what I do need is, let me open, if if I go to lessons, decimal print routine, I'm going to want to print a decimal value. Okay, and it will tell us, it'll tell us how fast our program is running. So down here, there, okay, now we have the ability to print values to the screen. So I could stick something in AX right now and call this and it would print. Okay, so let us see. Next, I think it's important in this routine, we're going to clear the interrupts. Now, routinely, I call CLI followed by HLT, which I'm actually doing here, because that clears the interrupts, just to make sure that no interrupts are interfering with our program. We're going to do the same up here. Now, there is a value that your computer keeps track of called the timestamp counter, right? And it basically tells you how many CPU ticks took place since the processor was reset. In our case, it would have been reset at the beginning of the program when we initialized our program. You could do other things to reset it, but that's another story. Okay, so and that is RDTSC, read timestamp counter. Okay, so now we have essentially grabbed our timestamp counter and have stored it into AX. Yeah, so now what I want to do is take a snapshot of that, because this program might, it should be multifunctional, and if we should happen to alter AX or something, we don't want to throw anything out. So we will put that into a variable. And by the way, this is a 32-bit value that we're capturing here. However, we're only working in 16 bits. Okay, so we're only really concerned with the lower byte of this value, you know. So let's say you got 1, 2, I'm sorry, whatever we got, 1, 2, 3, 4, 1, 2, 3, 8. All right, space 8, 16, 32, right? Okay, so it can read a pretty big value, right? But we're only maybe gonna end up with 512, you know, or 200 cycles have occurred, you know, so it'll be a pretty small number, 101 or something, you know, whatever. Excuse me. So in other words, we don't need all this part because we're working in 16-bit. We just want to get to the lower part of that, you know. So once we call that, we can well, we'll store it for now. Here, move it. I'll call this counter start. Okay, so the moment this is called, it's taking a snapshot of where our counter is. Okay, and then we're going to do a bunch of stuff and thereby increasing the counter. Okay, and then we will make a comparison to this value that we have stored in memory. Okay, so down here we can put some code that we want to benchmark down here. All right, and then I'll just say end code. All right, okay, and then we'll call the grab that timestamp counter a second time, right? And then this time we don't really need to store it. It is in AX, so we can just subtract from that the value, subtract the value that we have stored in here. This, yeah, put aside. this. Subtract AX that. Yes. One quick thing, let me just splice this in here. I'm not going to go back and redo the entire video, but I went and ran this and did not get the desired results. Here I mentioned this is a 32-bit value. We only want 16 bits of it, so I believe this solves our little discrepancy. This should have been word, and same thing right there. Yeah, that should fix it. It's going to change in a second because I'm not going to redo the whole video. Okay, but you want that in there. Counter start, yeah. And then, so now all we need to do is call this. Hang on. Take this and call it. Yeah. Did I say call it? And that should print out whatever, how much time has elapsed on whatever has happened in here. Let me just, for starters, here I'm just going to say a little minimal bit of code, BX, 1, 2, 3, 4, good to go. Okay, so now we'll save this and as our bean counter. Okay, I have saved it. You should do the same because this can come in handy for benchmarking little bits of code. Okay, so you've got that then, right? Okay, so then the next thing we want to do is go back to one of our little code samples, right? Why don't we start with my method, the old method here. And I don't need to go through all the printing the pixel to the screen and all that stuff. Hang on 1 second here. Blah, blah, blah. Copy some code over into here. There it is. Yeah, that's the code that we had. The example that I made. Running code, and then we don't have to do all the other stuff. This is the bit that we want to benchmark, you know, just a bit of the code that does the calculations and stuff. Okay, so let's test it. I'm going to save this. Okay, and let's see what happens actually. Save that and compile it and run. Counter start not defined. What? Oh, okay, hang on 1 second. Counter start, that was just, what was it? How did I end up writing over that? Here, I'll say. Counter, oh, that's right, I created a reference to it, and I intended to go down and declare the variable, and probably started talking about something else there. Okay, so I have my variable in place. Now what happens? Yeah, okay, so prints a pixel to the screen. Okay, it does a comparison on how many, takes a snapshot of the cycles, then prints a pixel to the screen, and then it does a comparison on how many cycles have elapsed. Okay, so make a note of this: 1, 2, 2, 5, 2. Okay, so now what I'm going to do is call my keymu shortcut on my B tab a second time, and 1, 2, 2. This is a different number. Why is that? Let me Alt F4 and call that again. And 9740. So this is very odd. We get inconsistent results. Each time we run it, we get a different value. Why is that? Well, because we are running under an emulator. And what this is telling us is how much time it took Windows to do a bunch of background stuff and then return us to our program in time to take the next snapshot, because that's the way Windows operates, you see. In order to get a more accurate reading of how this actually runs, we would have to run this at the boot level. Sorry about that. So it's the only thing running on our computer. Okay, so let me prepare for that here. What I'll do, we have our binary, so I can B-tab it like this. There's our code. We would like to boot off of this, right? Okay, so now for those of you who have watched the previous tutorial way back on how to make a bootable USB stick, then we will pick up where we left off. If not, you might want to do that. Now also, if anybody may have had some problems with that, I did notice I got 1 or 2 downvotes, and I was like, why would anybody vote this down? Well, I might have forgotten to mention, this is like doing video. It's one of those things, sometimes you just got to do it 6 or 8 times. Even I've done it a number of times, and I go back and I try it, and whoops. Oh, that didn't work. Oh, I got to do this. Oh, whoops, that didn't work. And, oh, right, I got to do that and this and the other. Oh, okay, now I finally got it to boot, and probably 1 or 2 people, and I do dislike that in tutorials when the author assumes everything went fine. So I'll try and cover a few extra bases in this episode. Okay. One, I'm going to copy this code, right? Let me just do it visually for your benefit. Copy that code. It is now in my memory. And I'm going to insert my USB flash. Okay. Now, Windows pops up and says there's a problem with the disk. Do you want to format it? As a matter of fact, I do want to format it, but first let me explain why. Yes, go away. Thank you for all the warnings. Okay, so here's what's going to happen. Got my code copied. I want that in the boot sector of my pre-formatted USB flash, as explained in the bootable USB video in this playlist series, right? So first I'm going to explain how you don't do it, or you can't do it. I'm going to go to open the disk, and there is our partitioned USB, right? As you recall, there's our 7 gigabytes, and we made a tiny 64 byte partition on it, right? Okay, so now I would like to, on there, note at the moment I selected this is grayed out, so I can't go there, and it says no. You must be in administrator mode, but I'm not going to go that route. There's actually a simpler way to do that, and that is, keep in mind we have some code that we put on there, that, some bit of our own assembly code, bootable, and so now we destroyed the directory structure, so Windows can't see it. Well, I'll just put that back. I will go here, and right here is my drive. This is very cool. I can put storage stuff on it, but if I select this one, it says it needs to be formatted. Well, okay, I'll just let Windows do that for me. I'll use a quick format and call this boot. Boot me. Start. Yeah. Okay, it's all wiped out and gone, and is still in a partitioned format, as we have created dual partition. So now I can just only format one partition, and it's all good to go again. So now if I go back to my tools over here, I can now go to the disk and deselect the read-only part, because we don't want to just read it. We want to write on boot me. And now when I go, okay, no problem. As you can see, Windows has filled it to the brim with who knows what. But we're going to, starting down here at our magic number, to select all that, and you can go Control B B as in boy, paste right, see, Control B, and then just save that. It says, are you sure, are you sure? Well, I am sure indeed. Okay, so next, as you know, it is impossible for me to boot up into just my USB flash and show the world, or is it? I have a trick up my sleeve today. I have installed a new setup where I can output my monitor to some hardware and capture that into a second computer, which hopefully should give me the ability to show you some things in the BIOS and how to boot properly off of the USB stick under my computer, which is a Dell. Okay, so let's go into a completely different mode here and see what happens. Okay, first things first, let's attempt to do a little hard restart here. I'm just going to shut down the system, and we'll see you on the other side. Now, if I were to just boot normally, it would go straight to Windows, which I accidentally did. Hang on. Now, if I were to boot normally, it would go straight into Windows, so I had to repeatedly pound my escape button. I am on a HP. I said I was on a Dell, that's my other computer. HP, you beat on the escape key. Other computers, it might be the F12 key. It's all hardware specific, so that depends on yours. This is my BIOS. So let me show you one thing. If I were to go, it says BIOS setup. If I go one to the right, one up, my boot order, so as you can see, Windows automatically sets itself to the top of the list. So we can bring that down, and then you would guess that in theory that means we would now boot off of the USB. Okay, so why don't we just give that a run and see what happens. Enter. Okay, I am rebooting. Whoops, I went to grub. See, I have a dual boot operating system, so I have a choice. So clearly that means that if it did that it did not recognize the USB. I thought it would, but no. Let's try it another way. I'm going to restart back into my BIOS again. This time beating on the escape key, so my HP enters BIOS mode. This time where it says boot device options, F9, we'll go in there, and my USB stick has brand name Geek Squad on it, and regardless of what I name it, the hardware is always called that. So to boot off that, I just hit enter, and there's my value. Okay, 640. So let's make a mental note of that. Okay, and then let's go over and get the other one then next, shall we? And bench test that one. If I do nothing, it takes me to my grub bootload. I have a choice between Windows and Linux. I'm going to go back to Windows. Back in our Windows operating system, let's test our other bit of code first. Before we do that, we'll want to locate our partition. It still has the label boot me, but if I click on there, it does not recognize it. So we'll just go ahead and format that. Again, boot. The boot. Quick format. Give you the boot. Deal. And then it is available storage. So let us go get our other code. I reckon that was, let me just copy from over here, over this. Yeah, method 2 using shifts and LEA. I'm going to save that. Okay, it is saved. First thing, let's get this over here. See what we got. Okay, arbitrary number. If I'm not mistaken, it will be different each time. Let me just QEMU it. Yeah, different number every time, right? Because it's telling us how many processes Windows is doing in the background. Okay, so we can now grab our binary. Whoops, I'm sorry. Here. There, binary. There it is, there it is. Click in here, Control A, Control C, and I have already formatted the disk, so it should be available there. Write only. There we go. Good to go. And we are gonna write on, Control B, Control. Yeah, good to go. So that is now bootable. Let's go do a benchmark test on that one as well, shall we? Beating on the key to enter my BIOS and circumvent Windows, which has automatically, of course, set itself to the top of the list. F9, there, Windows. There we go. 640. Ooh, missed it by that much. I'm afraid, while the theory was sound, excuse me, while the theory was sound, separating the values into two categories and then recombining them added an additional 4 bytes to the process. I'll talk a little bit more about that when I get back to Windows. Welcome to the real world. Jeez, I didn't realize being a diabolical mastermind could be so taxing, you know? So, here's the thing. I'm going to go to agner.org. They have some software optimization resources, interesting stuff. Down here, under instruction tables, it says download, but if you click normally, you can read the PDF. You can right click and download it, and these are some useful resources. Differences between terms used in the book. Oh, I should actually read that so I know what I'm reading. Okay, so different instruction sets that are available, you know, common commands that we all have in assembly, but the thing is there's different processors. Now, the person that submitted some sample code, it may actually run a little, might be shaving a few ticks on their processor, but not all processors are the same. I could tell you it would probably more than likely shave quite a few ticks on an older processor, an early Pentium or something like that, you know. I happen to be running Core 7, yeah, this one here, right? That one? Yeah, NASM. Yeah, and so a lot of those tricks that you're trying to do to speed things up, they've already thought of that. Yeah, they've done everything, every trick in the book they can think of to speed up their processors. So let's see, where are we? NASM, I believe it is down in here-ish or something. So let's see, which one are we on? NASM, nailed it. Okay, great. So here, if you find your processor, whichever one it may be, NASM, let me go to the top. Here, things about latency and stuff. Okay, here. But okay, so it has a number of banks, and they all behave some a little differently. But here's your main commands, like move R, one. Move to M or SR two. If you move SR to R, it takes up 6 operations. See, so a push to D, push D to I, 18. You see, so you can break it all down. You can look at your code and see exactly how many ticks your processor is going to use. Now, let's see if we get down to your multiplication. Now, these numbers on a modern processor are much smaller, than they would have been on an old one. Like I said, got every trick in the book in there now to speed up their modern processors. And whereas in the old days, in order to do multiplication, let's say if you wanted to do 10 times 10, it would add 10 plus 10 plus 10 plus 10 plus 10 plus 10, you see, to get to the result. Now, they're like, well, we could just do it the same way we did it in grade school. We'll have a multiplication table and go look it up. That only takes 1 or 2 ticks. So a lot of that has been circumvented. However, I did notice division can still eat up. A lot of ticks. So, in the case of, for instance, if you are dividing by an even number, 2, 4, 8, or 16, you definitely can save, by doing a shift right operation in binary instead. But for the most part, like I said, so you can do the numbers and do the math and add them up, or we've made a little utility that can test smaller bits of code one at a time and give you an idea of what's actually happening there. So there you go. Instruction tables, very useful resource for figuring out just how many ticks your processor is going to use up. There are other things you can do at the same resource here. Some useful stuff, just general read for ways to write your program, so it will run a little faster. I can show you some very simple general rules of thumb, though. Yeah, why don't I do that? One interesting example of a way to write code that runs a little faster. It's called loop unrolling. So this is kind of interesting. We'll go. I'm just gonna create a counter here, and we'll make a loop that repeats 10 times. Dot loop right there. And then we'll jump, not 0, to dot loop. I always forget that. There, make the label. Okay, and then say, down there we're going to just decrease CX in the loop. Okay, and then inside the loop we got some bit of code, whatever bit of code, that says blah blah and all that stuff, right? Okay, and maybe it could be fairly extensive, so you want to repeat it over and over. You make a loop. Okay, 10 times, nice. So alternatively, here, let me just copy this whole thing real quick. This is very odd. It didn't make sense at first, but if instead I took that same loop and did this, does the exact same thing, but it uses less ticks. And why is that? Well, because when we do this bit, that's like 3 ticks, right? Here we're doing 3 ticks 10 times. That's 30 ticks. Here we're doing 3 ticks twice. That's only 6. So you get the same result, but you end up not using as many ticks. So that's a general rule. But I mean, you don't have to write your code that way. It would be unreadable. In the gaming industry, I have some friends that work for a major game company, and what they do, that you have all your high power programmers, they write the code, and then when it's all finished and it's final code, then they bring in these specialists. It's an interesting job description, actually, that do all of this stuff, that take all the code apart and do everything the long, hard way. Loop. That's for your own convenience, right? You're not thinking, oh wow, and then, and then so somebody takes it all apart, and then now it's, instead of being a mile long, it's 10 miles long, and it takes overnight to compile it all into a program, but when it's all said and done, it runs faster. So very interesting science. Another method is inlining functions. Inlining functions. Yeah. So let me just make a quickie little subroutine. We'll say I'm going to move value into AL here. Say 2, whatever. And then I want to call some little subroutine. We'll just say dot print. Probably a bad example, since print is a subroutine we will reuse quite frequently, but just for argument's sake here. And then down here, I'll make the subroutine return, and we'll do something simple. Call that print, int 16. Okay, so let's say in your program, you've made this subroutine. That's great. That's for your convenience, but then you'll maybe only use it once. So then the point of making a subroutine has been negated, So technically then, if we just did cut that out of there and just put it in there, now that's going to use fewer ticks, you see. So subroutines, your functions and such, are more effective if you use them more than one time. Okay? The other thing, of course, is using efficient data types. If I create my word DB 4, right? That's kind of a waste, because I'm putting a small value in there, right? I'm sorry, DW. Storing a small value in a 16-bit register is going to take up more memory overall. It's not going to make your program any faster, of course, but if instead, you just can store that in a smaller value whenever applicable, then you're not going to be using up. Of course, these days you have gigabytes of memory, but when you're doing things in a loop, you can use up tons of memory inadvertently. So always using the smallest data type appropriate for your data. We've also briefly discussed how to store a binary bit, in a single value as well. So you could take an 8-bit value and store 8 individual Boolean, true or false values as well. Much more memory efficient. Yes. And of course, as I said, other things that you can do to speed up your program can be found at agner.org. optimize resources if you're working in C++. Here's another one, optimizing subroutines in assembly. So more interesting reading if speed is your interest. It's also, I suppose, good general read. A rule of thumb to go over things and trim a little time, a little space wherever possible. There you go. Like I said, that's like a specialized field. If anybody wanted to go into that, I know big software companies, they bring in the specialists after the big guys are done doing their thing to take them apart. So who knows? Could be a career for you, perhaps not. Anyways, there you go. Software optimization. I'd also like to take a moment to thank our minion that submitted the bit of code that was extremely useful. Win or lose, it wasn't a race. I've learned something from this. It took me in new and unexpected directions, which is the whole point of my going ahead and posting this series as a work in progress rather than completing the entire series and posting it in bulk as I've done in the past with my I have SUSE Linux, basically the same as this, but done in Linux. It's outdated, it's 10 years old, but then my assembly on the C64 series, Oh, and by the way, I just posted a new series of videos to watch with the sound off. Very cool. If you look in my playlists, I don't know if you ever want to just listen to some music, and watch some visuals, or you need to work, or keep it quiet late at night, while your significant other's sleeping or whatever, So I just tossed together a whole bunch of videos in a pile, and you can hit shuffle, and it'll play them randomly and everything. Yeah, so again, that was much appreciated, and that was the whole purpose, like I said, of starting this tutorial. I was getting nowhere on the usual channels, forums and all that in assembly for the longest time. It was just like, I don't know, trying to peck at it from the outside, and then I read an interesting article about Linus Torvalds, the guy that came up with the kernel for Linux, and interesting story. I can paraphrase. I don't know if it's 100% accurate. My take on it, was that that the guy wanted to. I bought a computer, wanted to learn how to program it, so he goes out and gets a book on programming, and as it so happened, it was a book on assembly programming, and he goes home and he disappears in his bedroom and kind of oblivious to the rest of the world, moving on to C and everything else, or maybe he had heard of it and he's like, I'm fine with what I'm doing, and then years later there was the GNU project, where all these programmers were trying to create a free software project, and they had written all these programs and everything, but the only thing that was missing was the kernel, and then one day this guy's like on one of these chat forums or whatever. He's like, oh yeah, I got this thing that I wrote so I could jump into 64-bit, and somebody's like, wait, what? Yeah, it's like, yeah, and it was the missing piece, to the whole puzzle, so I thought, well, that is interesting. What if I just, like, instead of constantly trying to approach assembly from the outside in, what if I just, like, toss myself in fully and not even work in other programming languages for a while, try to start working from the center out, and that kind of has actually been somewhat more productive so far, and definitely falling back on the old philosophy, of just setting the wheels in motion, and then like unexpected things happen, so much appreciated for the suggestions. They really helped me learn new and interesting things.